Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
The recent identification of a previously obscured population of dusty, star-forming galaxies fundamentally requires a reassessment of our established cosmic timeline. We are examining celestial bodies that formed approximately 1 billion years after the Big Bang.
Right. And when you contextualize that against the accepted age of the universe, which is roughly 13.7 billion years, finding mature galactic structures at that early stage is highly anomalous. This research originates from a major international collaboration. It involves 48 astronomers from 14 different countries.
Led by the University of Massachusetts Amherst.
Exactly. And the core significance of their findings is that we may need to significantly revise the standard timeline of cosmic history, specifically our models of galaxy evolution.
Because the existence of these galaxies challenges the presumed rate at which early stellar systems accumulated mass and heavier elements. But before we analyze the evolutionary implications, we need to address the observational challenge. Why were these galaxies effectively invisible until now?
It primarily comes down to the role of cosmic dust in astronomical observation.
Right, and we should define that carefully for anyone following along. We're not talking about standard particulate matter.
No, definitely not. Cosmic dust consists of heavy elements, primarily carbon and silicon. These are microscopic solid grains formed in the outer envelopes of dying stars. And this dust has a very specific interaction with the electromagnetic spectrum. It is highly efficient at absorbing high-energy, short-wavelength light.
Specifically, ultraviolet and visible light.
Precisely. So massive, newly formed stars emit copious amounts of ultraviolet radiation. But if those stars are embedded within a dense cloud of cosmic dust, that UV light gets absorbed by the grains. It never escapes the galaxy.
Which means optical telescopes, even highly advanced ones, cannot detect these specific galactic bodies.
Right. To an optical instrument like the Hubble Space Telescope, a dust-enshrouded galaxy registers as a void. The photons simply do not reach the detector.
But the laws of thermodynamics dictate that the absorbed energy must go somewhere. The dust absorbs the ultraviolet and visible radiation, which inevitably heats the dust grains.
Yes. And as the cosmic dust heats up, it re-emits that energy. However, the physics of energy re-emission means it does not come back out as high-energy ultraviolet light. The cooler dust radiates energy at much longer wavelengths.
In the infrared and submillimeter bands.
Exactly. So to bridge this observational gap, to actually see these galaxies, there is an absolute necessity for submillimeter and near-infrared instrumentation. You have to stop looking for the starlight and start looking for the thermal emission from the heated dust.
Which brings us to the methodology of this study. The researchers utilized a highly synergistic approach, combining data from two of the most advanced observatories currently in operation.
The Atacama Large Millimeter Submillimeter Array, or LMA, and the James Webb Space Telescope.
Let us break down phase one of this methodology, the submillimeter detection using LMA. LMA is situated in the Chilean Andes, which provides the extremely dry atmospheric conditions necessary for this kind of observation.
Right, because water vapor in Earth's atmosphere absorbs submillimeter radiation, so you need high altitude and low humidity. LMA has a specific capability to detect that faint infrared glow emitted by heated dust. In this initial phase, the array was utilized to survey specific regions of the sky, acting as a thermal detection grid.
And this survey led to the initial identification of approximately 400 bright, dust-rich galaxies.
Yes. 400 sources emitting strong submillimeter signals, indicating significant concentrations of heated cosmic dust. But LMA, while incredibly sensitive, provides relatively low spatial resolution. It identifies the coordinates and the presence of dust, but it does not easily reveal the stellar populations embedded within.
It provides the thermal footprint, essentially.
Exactly, which is why Phase 2 required the integration of data from the James Webb Space Telescope.
JWST operates primarily in the near-infrared and mid-infrared spectrum. So the researchers took the coordinates identified by LMA and examined the corresponding near-infrared data from JWST.
Right. Because near-infrared light has a longer wavelength than a visible light, it can penetrate through certain densities of cosmic dust that would otherwise block optical wavelengths. By correlating the ALMA submillimeter maps with the high-resolution JWST near-infrared images, they were looking for specific candidates located at the very edge of the observable universe.
And a result of this cross-referencing was the identification of approximately 70 faint, dusty galaxy candidates. Most of these had been completely undetected in previous surveys.
70 candidates is a significant sample size for this epoch, but the signals were incredibly faint. When you are observing objects that are nearly 13 billion light-years away, the signal-to-noise ratio is a major analytical hurdle.
Which necessitates phase 3 of the methodology, data stacking and signal confirmation. We should detail this analytical technique for you, as it is crucial to the validity of the findings.
Data stacking is essentially a statistical method used to enhance a faint signal. If you have 70 individual observations where the specific galactic emission is barely discernible from background instrumental or cosmic noise, analyzing them individually might not yield statistically significant results.
But if you align the observational data of all those candidates and mathematically stack them,
the random noise variations begin to cancel each other out. The noise is stochastic, meaning it fluctuates randomly above and below a baseline, but the actual emission from the galaxies, the true signal, remains constant in each observation.
Therefore, the objective of stacking these ALMA observations is to strengthen those faint, persistent signals. By isolating the constant data from the random noise, they can confirm the fundamental nature of the candidates.
And the result of this rigorous statistical process was the confirmation that these are indeed massive, dusty systems. They successfully isolated 18 specific dusty, star-forming galaxies and confirmed they formed almost 13 billion years ago.
It is a remarkable application of statistical astronomy. Now, we must transition to the broader implications of these 18 confirmed galaxies, specifically regarding galaxy evolution and what the researchers are calling the transitional phase hypothesis.
This is where the structural paradigm of cosmic history begins to shift. For years, astronomers have recognized a sort of missing link in galactic phylogeny.
Phylogeny in this context referring to the evolutionary development and diversification of galaxies over cosmic time.
Right. The hypothesis proposed by this study is that this newly discovered population of dusty galaxies represents a crucial transitional stage. It serves a bridging function between two distinct groups of early galaxies that were previously documented but seemed evolutionarily disconnected.
Let us categorize these distinct groups for clarity. We will refer to the earliest known systems as Group A, the early luminous population.
Group A consists of ultra-bright, highly active star-forming galaxies. Their defining characteristic is that they are relatively pristine. They formed roughly 13.3 billion years ago, which is very shortly after the Big Bang.
So within the first few 100 million years of cosmic expansion.
Yes. In terms of a developmental analogy, Group A represents the infant or highly young phase of galactic life. They are rapidly converting primordial hydrogen and helium into stars, but they have not yet produced significant amounts of cosmic dust.
Which is why they are so luminous in the ultraviolet spectrum. There's no dust to obscure their stellar emission.
Precisely. Now, skipping ahead in the established chronological models, we have what we can call Group C, the quiescent population.
These appear significantly later, roughly 2 billion years after the Big Bang. The characteristics of Group C galaxies are quite stark. They are massive, but they are considered dead galaxies because they have largely ceased all new star formation.
Right. The developmental analogy here is the old age phase. The gas reserves required to form new stars have either been exhausted or expelled from the galaxy, leading to a state of quiescent cessation.
The primary analytical problem has been the temporal gap between Group A and Group C. How does an ultra-bright, pristine, rapidly forming system transition into a massive, dead quiescent structure in roughly 1 billion years?
That speed of maturation defied existing models, and this is exactly where Group B, the newly identified dusty population, fits into the phylogeny.
The characteristics of Group B perfectly bridge the morphological gap. They formed roughly 1 billion years post-Big Bang. They are already massive, but unlike Group A, they are incredibly rich in metals and cosmic dust.
Using our developmental analogy, Group B represents the young adult phase. The intense star formation that began in the Group A phase has continued relentlessly. Over hundreds of millions of years, generations of massive stars have lived, fused heavier elements in their cores, and exploded as supernovae.
Distributing those heavy elements, the metals and the carbon and silicon dust, throughout the interstellar medium of the galaxy.
Exactly. So lead author Jorge Zavala interprets these three distinct groups not as separate, unrelated anomalies, but as chronological snapshots of a single evolutionary life cycle.
It is a continuous progression. It begins with ultra-bright creation, characterized by pristine gas and high luminosity. It evolves into massive, dusty maturity, where the accumulation of heavy elements obscures the galaxy. And finally, the star formation mechanisms shut down, leading to quiescent cessation.
And confirming this life cycle has profound implications for our broader cosmological models. The presence of such large amounts of metals and cosmic dust in galaxies of this specific age presents a direct challenge to accepted star formation rates.
Because current theoretical models do not account for such rapid and intense stellar generation in the early universe.
Right. To accumulate that volume of cosmic dust within the first billion years, the deduction is that stars were forming earlier and at a much higher intensity than our algorithms currently predict. The universe was far more active in its formative years than previously believed,
which necessitates a comprehensive revision of cosmic timelines. The theoretical models governing the physics of the early universe must be updated to account for this rapid accumulation of mass and dust.
The existing models of cosmic evolution are demonstrably incomplete regarding the speed of galactic maturation. We have to recalibrate the efficiency parameters of early gas accretion and star formation to align with these new empirical observations.
This research establishes a new baseline. For those analyzing the primary literature, these findings were published in the Astrophysical Journal letters.
The specific paper is titled LMA and JWST Identification of Faint Dusty Star-Forming Galaxies up to ZIS approximately 8 and their connection with other galaxy populations.
The ZIS roughly 8 designation refers to the cosmological redshift, which corroborates the extreme distance and age of these systems, placing them firmly within the first billion years of cosmic history.
It is also crucial to acknowledge the institutional context and the support structures that enable this level of data collection. The U.S. National Science Foundation provided significant funding, and as we noted, the project required extensive international cooperation.
Operating facilities like ALMA and coordinating observational time with space-based platforms like JWST demands a highly synchronized global scientific infrastructure.
It does. The logistical execution is almost as complex as the data analysis.
To summarize the scientific impact of this work, the core discovery is the successful unearthing of a hidden population of massive, dusty galaxies situated at the very edge of the observable universe.
And the primary consequence of this unearthing is the necessary rewriting of the timeline for star formation and galaxy maturity. We now have empirical data filling the critical gap between early luminous galaxies and later quiescent systems.
It validates the transitional phase hypothesis. However, in terms of future trajectories in astrophysics, this publication represents a beginning rather than an endpoint.
Absolutely. There is a definitive necessity for further research to rigorously validate this life cycle model. While the stacking technique provides strong statistical confirmation for the population as a whole, individual spectroscopic analyses of these dusty candidates will be required to map their precise chemical compositions.
We need detailed kinematic and metallicity data on a per-galaxy basis to refine the models further.
Yes, and this ongoing research will cement the role of submillimeter and infrared astronomy in resolving the history of the early universe. Optical surveys alone are insufficient. They systematically miss the heavily obscured phases of mass assembly.
The structural evolution of the universe began significantly earlier and proceeded much faster than established scientific paradigms had calculated. The objective reality is that the early cosmos was a highly efficient, rapidly maturing environment.
Which leaves you to consider a compelling variable. If a population of mature, massive galaxies could remain entirely hidden from our standard observational techniques for decades, merely obscured by their own cosmic dust, we must mathematically assume our current census of the early universe remains critically incomplete.
The implication being that even older, structurally complex systems may still be evading detection in the infrared background, waiting for next-generation instruments to identify their thermal signatures.